So we're all familiar with learning thermostats that have been introduced in recent years. I'm here to tell you that these thermostats don't save a lot of energy, and that a system that helps users save energy does much better. I'd like to start by reminding everybody why this is an important problem. Thermostats are used to control the heating and cooling systems. HVACs use a lot of energy. In fact, 10% of the total energy consumption in the United States is by heating and cooling systems alone. So what can we do to address this problem? In homes, we can take advantage of the following two scenarios. When occupants of a home are typically away and a home is unoccupied, and when occupants of a home are asleep, we can use a more energy-efficient temperature setting. We're asleep for about 7 hours a night, and on a typical workday, we're away for 8 hours or more. Thus, 2/3 of a day is such that we can save energy. So most of us here believe that technology can help solve this problem. So let's look at some of the solutions that have tried to address this. So the first set of solutions are based on energy feedback. What I mean by this is when homeowners receive feedback of their energy use by looking at their utility bill, for example, they're prompted to go and change their thermostat settings in order to try and save some energy. So programmable thermostats allow them to do so. These thermostats allow users to monitor their energy usage. Now, studies have shown that these thermostats have a few challenges. Most people don't know their schedules, especially in multi-occupant homes. Studies have shown that people find thermostats difficult to use. And some people just lack motivation to reprogram their thermostat, especially if their energy bill isn't too high. So the next set of solutions tries to address these challenges. Learning thermostats. Learning thermostats like the Nest or the Smart Thermostat automatically create temperature schedules so that homeowners no longer need to do it. Thus, learning thermostats take actions on behalf of the user. Now, recent studies have shown that learning thermostats don't save a lot of energy as well. So our approach lies in the middle of this spectrum with EcoCoaching, where we believe that schedule recommendations that are sent to the user, and the user has to act upon these schedule recommendations, and that this would save more energy. So this system basically decides actions that the user can take, but leaves them in control. So you might wonder why this might work, because while EcoCoaching thermostats monitor energy and decide on actions that a user can take, they do less than autonomous thermostats. They don't take the actions for the user. Well, the reason for this is that both EcoFeedback and fully autonomous solutions are counterintuitive to each other. As soon as you take away control from a user, they no longer feel responsible for their energy consumption, and therefore energy feedback of any kind is useless because they no longer respond to it. So we believe that making people smarter will save more energy than making just smart thermostats. So to evaluate this hypothesis, we created a system called ThermoCoach, and I'm going to go over the details of ThermoCoach. So we instrumented a home with Bluetooth, low energy tags, and Z-wave motion sensors. So let's look at some sample data. In this graph here, time is along the x-axis. So the blue line at the bottom is data from the Bluetooth sensor. Now we assume that whenever occupants of the home left the home, they carried their keys with them. So a high value indicates that the occupants are home, while a low value indicates that they are away. So the pink shaded regions are times when the occupants are home, and the white region is when the occupants are away. Now the next interesting state is sleep. So we define sleep as any period during the night where we know the occupants are home, but they're not active. So this purple region here denotes the sleep event. And we used motion sensor data that's indicated by the top two lines in this graph. So whenever we see no activity at nighttime, we say that the occupants of the home are asleep. Now, this occupancy data is collected over several days. So this is an occupancy data for another. This could be the data for another day, and so on. We then use this data to create a histogram, where each point in this histogram represents the percentage of times the home is in a given state. So for sleep, most of the higher values would be, in this case, between midnight and 9 a.m. We do the same for awake, which would look like this, since the data shows that the occupants of the home are mostly awake between 9 to 5. Now, let's look at what potential schedule for this home could look like. We could say that the occupants of the home wake up at 7 in the morning, and we set the temperature to 75 degrees Fahrenheit. Now, we can say that the occupants of the home leave for work at, say, 9, and we set a setback temperature of 83 degrees. And they come back typically at, say, 5 p.m., and we set the temperature back. And if they typically go to bed at midnight, we can say that we'll set the temperature to 79, which is a good sleep setback. So how does this schedule fare? Well, we want to know how much energy it can save, as well as what impact it has on user comfort. So let's start with energy cost. We measure energy cost, or the cost of conditioning a home at a particular set point as a relative cost. So basically, it's relative to the cost of conditioning the home at the most expensive set point in the schedule. So what I mean is, if this blue bar is the cost of conditioning the home at 79, the cost of conditioning the home at 75 is going to be more, indicated by the darker region. It's going to be less for 83, more for 75 again, and so on. And then we add up all these values to give an energy cost, a single energy cost value for the schedule. Now, we define the next term as mist time, which is an indication of user comfort. It's basically the average minutes in a day that the user may be uncomfortable. So let's look at an example here. We see here that we assume that the occupants of the home typically come home at 5, but there could be days where they come home before 5. Similarly, we assume that they go to bed around midnight, but they may actually be awake longer. So the sum of these times total is the mist time for this schedule. Now, we create all possible schedules for a particular home. And now, once we have all these possible schedules, we choose 3. 3 with minimum energy cost, but acceptable mist times. So we choose one schedule which has low mist time, so it's more comfortable, but might save less energy. And we define a threshold for the mist time as 10% of the total active time in the day. Similarly, we choose 2 other schedules with 20 and 30% of the active time. These schedule recommendations are then emailed to homeowners. So here they can see the schedule recommendations. They also get energy feedback on how much energy they can potentially save, as well as the impact on their comfort. This here is ThermoCoach's web interface. Users can, again, view the schedule recommendations. They can look at their occupancy trends for their home. They can modify a schedule. And they're given feedback on how much energy the schedule could potentially save. Now, to evaluate this, we recruited about 39 homes in Charlottesville, Virginia. We deployed over 200 motion sensors, 39 Nest learning thermostats, the same number of Wi-Fi routers, over 117 Bluetooth low energy tags, and over 180 Raspberry Pis running the smart home platform Piloteer that was used to collect and manage sensor data. So how did we evaluate this system? Well, we performed what's called a panel study, where repeated measures of the same samples are collected over time to compare how a solution works. The samples in a panel study are divided into two groups, a control group and a treatment group. The treatment group is the group to which the solution is applied. Somewhere during the study, an intervention is performed. An intervention is the point in time where the solution is applied to the treatment group. So all the data before intervention is called the pre-intervention data, and all after intervention is called the post-intervention data. Now, to know how well this solution did, the panel studies use a difference of differences approach. So we calculate the mean value of whatever we want to measure. I'm going to call it the outcome variable. So M1 is the mean value of the outcome variable for the control group before intervention. And M2 is the mean value of the outcome variable post-intervention for the control group. Similarly, we define M3 and M4 for the treatment group. We then calculate the difference in the mean values for the control group and the treatment group, and the total treatment impact is given by the difference of these differences as the difference between the mean values of the control and treatment group. So in order to see how EcoCoaching does with the other two solutions, we divided the homes randomly into three groups. We used the Nest Learning Thermostat for all three groups, and we turned off the learning features of the Nest for the EcoFeedback and EcoCoaching group. During intervention, Nest energy reports were sent to all homes in the study, which basically has information about how long the air conditioning was on for that home, as well as energy saving tips from Nest. For the EcoCoaching group, they received schedule recommendations from ThermoCoach as well. So we performed this study over 3 months in the summer. We began data collection around June 30th. On July 21st, we performed an intervention, which is peak summer in Virginia. And we ended the study somewhere around September 9th. So let's see how these various homes did throughout the study. The first graph here represents the data for the EcoFeedback Group. In this graph, we have time along the x-axis. Each cell here represents the estimated cost of conditioning the home on that given day. This red line here on the right indicates the day when intervention was performed. I'd like to point out that lighter colors in this graph are good. Lighter colors indicate lower energy cost. These white cells here are days where we lost sensor data. So let's look at this home here. So 2 homes in this group changed their schedule just based on energy feedback. And this home saw significantly reduced their energy usage post-intervention. Now, let's look at the autonomous group here. In this group here, we see that most homes did not see any significant change in their energy use. And in fact, one home did worse after intervention. We're not quite sure why. And finally, let's look at the ThermoCoach group. Post-intervention, about 8 homes chose schedule recommendations and saw a significant decrease in their energy cost. This is one home here. Here's another home. It's important to note that we saw a clear weekday-weekend trend in the data for most of our homes. So in total, about 8 homes reduced their energy costs. So how do we summarize these results? Well, when we compared EcoCoaching to EcoFeedback, we saw that EcoCoaching reduced energy costs by 5%. When we compared EcoCoaching with autonomous groups, EcoCoaching reduced the energy costs by 12%, so it did better than the autonomous group. And when we compared the autonomous group with just EcoFeedback, we saw that it increased energy costs by about 8%. So I just want to take a moment to explain this result here. So when we compared the energy cost or the energy usage of homes in the EcoFeedback group, that's the first group, with the autonomous group, we saw that even before intervention, these homes, the homes in the EcoFeedback group used more energy, and that over time, the energy usage of the autonomous group did not change much over time. So therefore, it looks like the autonomous group did significantly worse than the EcoFeedback group. So in addition to figuring out, in addition at looking at the cost of conditioning a home, we also looked at average degrees overridden. What this is whenever we calculated for a given day the average temperature changed by the user that was not part of a schedule. So we would like to think of this as an indication of how comfortable the users were with the recommended schedules. So we see that EcoCoaching reduced the number of overrides by 47%, while when compared to autonomous groups, it reduced the number of overrides by 45%, and the autonomous group reduced the number of overrides by 3%. So I'd like to conclude with this slide. So ThermoCoach saved more energy than both the energy of the EcoFeedback group as well as autonomous thermostat group. And I'd like to leave you with this. As we take away control from the user, we also take away responsibility from the user. And as soon as we do that, they'll no longer feel responsible for their energy use. Thus, the future smart thermostats lies in making people smarter and not making smart thermostats. And I'd like to conclude by thanking my co-authors, as well as Eva, who helped us design the user interface, and John, who helped with the implementation of Pilot Year. That's it.